How Newton might interpret gravity was sufficient to permit us to fly from the Earth to the Moon. Get yourself lost in the ticking hands of time, contemplating whether we might construe it as merely the tip of the temporary iceberg. Discovery isn't simply a hypothesis. A key could open the doors to the secrets, revealing a universe within the universe, more unpredictable and inspiring than we ever imagined. Have you ever considered how Brian Cox's new hypothesis challenges our traditional conceptions of time? What are some possible implications for our perception of reality? Join us on a fascinating investigation through the archives of time itself as we delve into Brian Cox's recently uncovered, remarkable hypothesis on the nature of time in the vast universe around us. There are secrets that need to be exposed, and some of these secrets involve confusing concepts related to time and gravity, fundamental parts of our reality. Imagine a world in which time behaves strangely, where it can either slow down or accelerate. Additionally, the force that keeps us on the ground may not be what it appears to be. This is the realm of Albert Einstein's theories of relativity, in which our interpretation of time and gravity veers off in unexpected directions. A notable figure, Albert Einstein, gave us a better way of looking at the universe through his theories of relativity. His work laid the foundation for understanding how time behaves under various circumstances, particularly when traveling at incredible speeds. It all started in the early 20th century when Einstein introduced two groundbreaking theories, the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, changed how we interpret existence. In simple terms, it tells us that the laws of physics remain the same for all observers who aren't accelerating, regardless of their motion. This theory opens up the possibility of relativistic effects, including the well-known idea that time can expand or slow down under certain circumstances. One captivating thought experiment used to demonstrate time dilation is the light clock. Picture yourself in a spaceship moving incredibly fast, nearly at the speed of light. Inside the spaceship, a beam of light bounces between two mirrors, perpendicular to the direction of motion. According to the laws of physics, the speed of light is constant for everyone who observes it, so the light beam must appear to travel in a diagonal path. Now for the interesting part. The time it takes for the light beam to travel its path should be the same for both the observer inside the spaceship and the one outside. However, since the path is longer for the outside observer, it appears as if it would take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer moving relative to the stationary observer. Understanding how things change when they move fast, known as relativistic effects, is more than just a theoretical idea. Scientists use massive machines called particle accelerators, like the Large Hadron Collider, to make particles travel at nearly the speed of light. When things move this fast, we need to consider time differently to make accurate predictions and measurements. Albert Einstein's special theory of relativity, developed in 1905, altered the way we see the universe, particularly regarding time and motion. This theory challenges our normal intuition. It declares that the physical laws are the same for everyone, whether they are moving or not. This is different from our everyday experience, where we might think that if something is already moving and we add more speed, it just gets faster. But Einstein's theory says there's a maximum speed that nothing can exceed, the speed of light. From this perspective, events that seem to happen at the same time for us may not appear that way to people moving close to the speed of light. Another consequence of this new way of seeing things is length contraction. This means that if something is moving, it looks shorter in the direction it is traveling when viewed from a stationary perspective. Then there's Einstein's famous equation. E equals mc squared. This equation shows that energy and mass can be transformed into each other, which is a big deal for understanding the behavior of particles moving at extremely high speeds and for processes like nuclear reactions. In reality, special relativity isn't just an abstract theory, it's something we use in everyday technology, like GPS. When GPS satellites send signals to your device, they are moving, so time acts slightly differently for them. If we didn't account for this time dilation effect, GPS-based navigational calculations would be inaccurate. Special relativity assures us that time is not the same for everything and everywhere, it depends on how things are moving. This idea challenges our conventional understanding of reality. But there's more. In 1915, Einstein developed the general theory of relativity, which delves deeper into the connection between gravity and the structure of the universe. It overturns the old idea that gravity is just a force that pulls objects from afar. Instead, it tells us that gravity happens because spacetime itself is curved or bent. Imagine spacetime like a big, stretchy blanket. When something heavy, like Earth, is placed on it, the the blanket bends. If you place something smaller nearby, like a ball, it will roll toward the dent. This is similar to how objects behave due to gravity, not because of a mysterious force, but as a response to the bending of spacetime. This new interpretation of gravity gives a solid explanation for how objects move in our solar system, like how planets orbit the sun. It replaces the old belief that gravity simply pulls objects together, which struggle to explain planetary motion. Instead, space and time are curved, like a flexible fabric, and this better fits what we observe. A major moment confirming general relativity occurred during the solar eclipse of 1919. Sir Arthur Eddington led a team to observe how light from distant stars bent as it passed near the sun. The observations matched Einstein's predictions precisely, establishing the validity of his theory. Just as motion changes how we experience time according to special relativity, gravity also affects time. In regions of strong gravity, time moves more slowly compared to areas with weaker gravity. If you were standing near a massive object like a black hole, your clock would run more slowly than one set farther away. General relativity also introduces the concept of black holes, regions where gravity is so intense that nothing, not even light, can escape. The boundary around a black hole is known as the event horizon, a point of no return. Once something crosses this boundary, it is pulled into the black hole with no chance of escape. Einstein's general theory of relativity has enormous implications for how the universe is structured. Initially, he added something called the cosmological constant to his equations because he believed the universe was static. However, we later discovered that the universe is expanding, and Einstein called this assumption a huge mistake. One important consequence of general relativity is its explanation of the universe's origins. The theory also predicts the existence of gravitational waves, ripples in the fabric of spacetime caused by massive objects moving at extreme speeds. The evolution of our understanding of gravity. While Einstein's theories of relativity have stood the test of time, scientists like Brian Cox continue to explore whether our current understanding of gravity is complete. Could there be deeper layers to this force, perhaps tied to quantum mechanics or even undiscovered dimensions? One of the biggest mysteries in modern physics is the apparent incompatibility between general relativity and quantum mechanics. General relativity explains gravity on a large scale, governing planets, stars, and black holes, while quantum mechanics describes the behavior of the smallest particles in the universe. However, when we try to merge these two theories, especially in extreme environments like black holes or the early universe, mathematical inconsistencies arise. This has led scientists to search for a more unified theory of reality, one that seamlessly incorporates both gravity and quantum mechanics. The quest for a theory of everything. Physicists have proposed several potential candidates for this ultimate theory, including 1. Quantum gravity, a theoretical framework that attempts to describe gravity within the rules of quantum mechanics. This would help explain what happens inside black holes and at the moment of the Big Bang. 2. String theory, a radical idea that suggests the fundamental building blocks of the universe aren't particles but tiny vibrating strings of energy. String theory also proposes extra dimensions beyond the familiar three of space and one of time. 3. Loop quantum gravity, another attempt to reconcile relativity and quantum mechanics, suggesting that spacetime itself is quantized, meaning it has a discrete, granular structure rather than being smooth and continuous. 4. Emergent gravity, some physicists, including Eric Verland, propose that gravity isn't a fundamental force at all but rather an emergent property of spacetime, much like temperature emerges from the collective behavior of molecules. The role of black holes in unlocking new physics. Black holes remain one of the greatest testing grounds for new physics. The information paradox, posed by Stephen Hawking, suggests that if information about matter falling into a black hole is lost forever, it contradicts quantum mechanics. Scientists are now exploring solutions such as holographic principle, the idea that all the information contained in a three-dimensional space might actually be encoded on its two-dimensional boundary. This could mean that black holes function like cosmic holograms, where information is preserved at their event horizon. Hawking radiation, a theoretical form of radiation emitted by black holes, which suggests they can slowly evaporate over time. If proven, it would confirm that black holes don't hold onto information indefinitely. Wormholes and time travel. Some interpretations of relativity suggest that black holes could be connected by wormholes, acting as shortcuts through spacetime. While still speculative, these ideas fuel research into whether time travel or interstellar shortcuts might be possible. How Brian Cox challenges traditional views. Brian Cox is known for making complex scientific ideas accessible to the public, often presenting new ways of thinking about time and the universe. He explores questions like, is time an absolute entity, or is it an emergent property of the universe? Could the flow of time be an illusion, with everything existing simultaneously in a block universe? Does gravity behave differently at quantum scales, pointing to undiscovered physics? By questioning these ideas, Cox and other physicists push the boundaries of our understanding, suggesting that while relativity is a crucial part of our knowledge, it may not be the final answer. The future of gravitational research. Scientists are now using advanced experiments to test the limits of gravity. LIGO and Virgo observatories continue detecting gravitational waves, providing new insights into black holes and neutron star collisions. James Webb Space Telescope is helping us study the early universe, possibly revealing new aspects of gravity at cosmic scales. Quantum experiments with cold atoms aim to observe quantum effects in gravitational fields, potentially leading to new discoveries. Conclusion. Our journey through time, gravity, and relativity has transformed the way we see the universe. From Newton's laws to Einstein's revolutions and now the search for quantum gravity, science continues to evolve. As Brian Cox and others explore the frontiers of physics, we may soon uncover even deeper truths about the nature of reality itself. The way we think about this fundamental force is changing. One theory challenging conventional gravity is called modified Newtonian dynamics, MOND. MOND suggests that gravity behaves differently at low velocities, especially in universes that do not require dark matter. Instead of adding invisible matter, MOND proposes that gravity becomes stronger at low velocities. The gravity debate also involves mysterious dark matter and dark energy, which were introduced to explain certain phenomena in space. Critics argue that these may not be necessary and that alternative ideas can explain what we observe. Some researchers who disagree with Einstein's gravity theory explore other possibilities, such as theories involving unknown particles or forces that could alter or contribute to our understanding of gravity. It's important to understand that in science, groundbreaking ideas aren't overlooked, they are carefully tested to see if they make sense. For example, Einstein's idea of time in four-dimensional space, where time travel into the past may be limited by the speed of light, has been creatively explored alongside ideas like wormholes and shortcuts. Stephen Hawking's chronology protection conjecture proposes that time travel into the past seems unlikely from a physics perspective. Ongoing tests and observations check if these new theories can explain things like the strength of gravity in a way similar to what we already know. While alternative ideas have been discussed, none have convincingly replaced the well-established principles of gravity. Questioning and challenging ideas are vital parts of how science learns new things, leading to further investigation and a better understanding of the universe. General relativity and space travel. In the world of gravity theories, general relativity remains the most significant and successful one. Despite challenges and alternative ideas, it consistently performs well in tests and explains various phenomena, such as how planets move and how light bends around massive objects. General relativity stands strong because it is both simple and capable of explaining a wide variety of phenomena. As discussed earlier, Einstein's special theory of relativity suggests that time behaves differently depending on how you're moving. Now, let's explore how this idea affects real-world scenarios, especially in space travel. Space travel is exciting but challenging because space is vast. According to Einstein's theory, the speed of light is the fastest anything can go. This makes traveling between stars a huge challenge, even with cutting-edge technology, because of the long time scales involved in reaching the nearest stars. Consider the famous twin paradox to understand what happens to time when traveling in space. Imagine this. One twin stays on Earth. The other twin travels to a distant star. When the space-traveling twin returns, they find that less time has passed for them than for their twin on Earth. This means they have, in a sense, traveled into the future. Time is crucial for space travelers because the longer the journey, the more time slows down. If astronauts travel to nearby stars at high speeds, time dilation will cause them to age more slowly than people on Earth. While it might sound like science fiction, it's a real effect predicted by the theory of relativity. Imagine if humans sent a crew to a nearby star system. Because of the vast distances involved, the journey might take many years, even with fast spacecraft. For the astronauts, time would feel slower because of time dilation. Meanwhile, on Earth, much more time would have passed. Time dilation doesn't just affect living things, it also affects technology. Computers and communication systems on spacecraft must account for time dilation to ensure accuracy and proper functioning. The challenges of space travel. High-speed space travel presents many challenges. Prolonged isolation from Earth. Exposure to cosmic radiation. Psychological effects of extended missions. We can see the effects of time dilation in our everyday lives, too. The Global Positioning System, GPS, depends on the precise timing of signals from moving satellites. Since these satellites experience time dilation, it's crucial to account for these effects in GPS calculations. Without doing so, the accuracy of navigation systems would be significantly affected. The arrow of time. Why does time move in one direction? Time governs our lives, moving from the past to the present and into the future. This one-way flow of time is fundamental to our existence. But why does time have this one-way nature? To understand this, we look at entropy, which measures disorder or randomness in a system. Entropy is tied to the arrow of time, and it tends to increase over time, making time flow in one direction. The second law of thermodynamics states that in any isolated system, total entropy will either increase or remain constant. In simple terms, entropy naturally increases and does not decrease on its own. We can see this in everyday life. Imagine a neatly arranged deck of cards. 1. If you shuffle them, they become messy and random. 2. Ice melts into water, increasing disorder. 3. A stirred cup of coffee mixes and becomes more chaotic. This transition from order to disorder demonstrates how time moves forward. However, at the microscopic level, the laws of physics allow things to move both forward and backward in time. This idea is known as time reversal symmetry. The reason we don't see time moving backward in our everyday world has to do with initial conditions. On a cosmic scale, the universe has been progressing in one direction since the Big Bang. It began in a low-entropy state and has become increasingly disordered over billions of years, forming galaxies and stars. Scientists are still trying to understand why the universe started in such an ordered state. Even in quantum mechanics, which deals with tiny particles, there is an arrow of time. The way particles change over time seems reversible, but when we observe them, things become irreversible. The psychological arrow of time. Physicist Brian Greene suggests that the arrow of time is not just a physics concept, it also applies to our perception of time. We remember the past. We experience the present. We think about the future. This mental arrow of time is tied to the physical arrow of time in the universe. It has profound philosophical implications, shaping how we understand reality. Without this one-way progression, cause and effect wouldn't make sense, and the world as we know it would be completely different. Could time dilation make time travel into the future a reality? Given what we know about Einstein's theory of relativity, do you think time dilation could make time travel into the future a reality for space travelers? The possibility of time travel into the future. Time dilation, as predicted by Einstein's theory of relativity, shows that traveling at high speeds or being in a strong gravitational field can significantly slow down time for the traveler relative to those who remain in a different frame of reference. This naturally raises the question: could time dilation allow astronauts to travel into the future? The answer is yes, at least in a practical sense. If a spacecraft could travel close to the speed of light, say, 99.9% of it, time for those aboard would slow dramatically compared to people on Earth. For example, if astronauts traveled at this speed for 10 years in their own time, hundreds of years could pass on Earth. When they returned, they would have effectively leaped forward in time, while aging far less than those who remained behind. This is a form of one-way time travel into the future, and it is not just theoretical, it has been experimentally confirmed using atomic clocks on high-speed aircraft and satellites. These clocks, when compared to stationary ones, run slightly slower, just as relativity predicts. Limitations of future time travel. While future time travel seems feasible with high-speed spaceflight, there are significant challenges. 1. Energy requirements. Accelerating a spacecraft close to the speed of light would require enormous amounts of energy, far beyond our current capabilities. 2. Engineering feasibility. We currently lack the technology to build spacecraft that can approach such speed safely. 3. Human factors. Extended space travel involves risks such as radiation exposure, psychological effects, and resource limitations. 4. No return to the past. Unlike fictional time machines, relativity does not allow backward time travel, at least according to our current understanding of physics. Can we travel back in time? While time dilation makes future travel possible, traveling backward in time is a much deeper challenge. Some speculative theories propose ways it might happen, but none are confirmed. 1. Wormholes. These are theoretical shortcuts in spacetime, sometimes called Einstein-Rosen bridges. If they exist and could be stabilized, they might allow travel between different points in time. 2. Closed time-like curves, CTCs. Solutions to Einstein's equation suggest that certain spacetime structures could loop back on themselves, allowing time travel. 3. Tipler cylinders. A hypothetical rotating cylinder of infinite length might, in theory, allow time loops. However, such an object is unlikely to exist. 4. Hawking's chronology protection conjecture. Stephen Hawking proposed that the laws of physics might prevent backward time travel, ensuring that paradoxes, such as the grandfather paradox, do not occur. The grandfather paradox and other time travel paradoxes. One of the biggest problems with backward time travel is the grandfather paradox. Suppose you traveled back in time and prevented your grandfather from meeting your grandmother. This would prevent your parent, and therefore you, from being born. If you were never born, how did you travel back in time in the first place? This paradox suggests that either backward time travel is impossible, or the universe somehow prevents paradoxes, such as through the many worlds interpretation, where an alternate timeline forms. The future of time travel research. Scientists continue to explore the nature of time through both theoretical and experimental physics. Some current areas of research include quantum gravity. A theory uniting relativity and quantum mechanics could reveal new insights into time travel. Exotic matter. If negative energy or exotic particles exist, they could theoretically stabilize wormholes. Advancements in space travel. As our technology improves, high-speed interstellar travel could be tested, pushing the limits of time dilation effects. Final thoughts. While time travel into the past remains uncertain, traveling into the future is a reality, at least in small increments due to time dilation. If humanity develops near-light-speed travel, astronauts could leap centuries or even millennia forward in time while aging only a few years themselves. Do you think we will ever develop the technology to achieve significant time travel into the future?